the order of the graph. And so yeah, on Hilbert's pebbling page, I just kind of listed a few of some of the more obvious results. If I have two vertices, V and W, and the distance between V and W is L, if I then place 2 to the L minus 1 pebbles at W, then there are not enough pebbles, if you will, to move to V, right? So again, as a simple pyrotechnic example, W and V, the distance is 2, right? So 2 to the 2 minus 1, if I place 3 pebbles at W, right? If I try to make a move, I have to remove one pebble, slide the other pebble along the path. I now no longer have enough to get to V, right? And so this actually is a nice sort of basic result that gets used in a lot of the proofs for different pebbling numbers or bounds on pebbling numbers. I should say in general this is not an easy problem to figure out the pebbling number for graphs. And so again, just a couple of other results that you can find on Hilbert's page. The important thing here is the last bullet item. For those graphs in which the pebbling number is the order of the graph, they're referred to as Class-0 graphs. Right? So a Class-0 graph is any graph in which the pebbling number itself is n. And so there's been a lot of research done on, what are the Class-0 graphs.
Why is that minimal? I'm sorry, I'm trying to understand the first bullet. You say you've got to have at least as many pebbles as the number of nodes.
Yes.
Why is that?
Because the pebbling number, in a sense, the pebbling number has to work for any target vertex. So you may find an arrangement that works for one particular vertex, but it has to work no matter what the target vertex is. So if I have fewer than n pebbles, and I'm trying to basically use those pebbles to get to any other vertex. In this particular example, since I've got 5 vertices, if I have 4 or fewer pebbles, I can come up with an arrangement where I have just one vertex, or one pebble per vertex.
You could, but you could also try a different starting arrangement, which might work better than that one.
But then it has to work no matter what the arrangement. So for every arrangement of 4 pebbles, I need to be able to get to the target vertex. Yes.
I think there's a word missing in the first sentence.
You're getting all the extra credit today. Yes. You're right. I'm sorry. Yes. For every arrangement. It helps, I suppose, if I don't have my typos and critical points.
Sure.
So, yes, I apologize. So for every arrangement, I need to be able to get to any target vertex. So yes, that's why the order is going to be the minimum, or the lower bound for pebbling numbers. And so again, if I have a graph that has a pebbling number that's the order of the graph, we're going to refer to those as Class-0. And so we know a few Class-0 graphs. Come on. There we go. All right. So of course, complete graphs are Class-0 graphs, because no matter how I make the arrangement, and no matter what the target vertex is, I'm one step away, right? So even if I don't place all the vertices, all the pebbles on each vertex, if there's an open vertex, that means there's got to be at least one vertex that has at least 2 pebbles on it, and it's one move, and that's all I need, right? So I can get to that target vertex. Of course, all the other ones here, I already have a pebble there, so if they're the target vertex, I make 0 moves, and I'm done. The Petersons Graph, oddly, once again, if you're looking for an example, the Petersons Graph is a Class-0 graph. The 5 cycle is a Class-0 graph, but none of the other cycles, obviously, or interestingly, are not. And so actually, some of the other pebbling numbers, again, you can find all these results out on Hilbert's page, for a path, right? So if we just have a path, the pebbling number is simply 2 to the n minus 1, right? And if you just think about, again, what's the worst arrangement that you can have? All the pebbles lined up on one end vertex, and you've got to get all the way to the other end. And so you need at least, if you sort of count backwards, right, you've got 2 to the n minus 1 of those. And they also have identified the pebbling number for trees as well. And so again, trying to find the pebbling number can be a very difficult task in general. And they often simply have bounds on what they think the pebbling number is for certain graphs.
Do you know how many Class-0 graphs there are with n nodes? That would be a secret.
Yes, yes.
Oh, connected,
Yes.
connected Class-0 graphs with n nodes.
Interesting, yes.
I
Give me
think
1 second, I'm going to write this down, because by the time I'm done, yes. I'm now at that age where I, forget things.
What's the Peterson graph?
Oh, I'm sorry, what is the Peterson graph? And again, I always sort of imagine taking a complete graph on 5 vertices and separating, if you will, each vertex. Right, so you've got a 5 cycle on the outside, and then the alternative 5 cycle on the inside, and then joining the appropriate edges.
The most famous graph.
Yeah. Yes. It's 3 regular, meaning every vertex has degree 3. And generally, the rule of thumb is if you're looking for an exception to the rule, Peterson graph. Okay, great. Thank you. So we now have another. So I have to amend my earlier statement. We are talking a little bit about OEIS. So, all right. So what's the problem we're working on? Let's get through this. There we go. All right. So again, there are some of these results we used to get to what we were after. A couple of general results. If the diameter of a graph is 2, and the connectivity of the graph is 3, right? So at least 3 vertices need to be removed. Then G is class 0. Actually, this tends to be a very well-known and significant result. And so because of that, in the literature you often see it abbreviated as 2D3C to represent a diameter of 2 and 3 connected. And I should point out that 2D3C is in fact a stronger condition than that of class 0, right? So if we know it's 2D3C, then we know it's class 0. And although it's a sufficient condition, it's not necessarily, it's not a necessary condition. And of course, this result is an example of a kind of graph that meets that statement, basically. And so if you have a function calling k of d that satisfies those bounds, and G is a graph of diameter d, then it is not 2D3C, but it is class 0. Okay, with that in mind, what we were dealing with in this paper was something that we called K-class 0. And so we kind of turned it around and said, suppose that we've got a graph, a big graph, and I want to partition the edges in some way. So I want to do an edge partition of the graph. So each partition has the same vertex set, but I partition the edges. But I want to partition it in a way that each subgraph, each partitioned subgraph, is itself class 0. And if I can do that k times, if I can do a k partition, then I'm going to refer to the original graph as k class 0, right? Okay. And so actually, we wanted to prove, or we're looking for k class 0 type graphs. And some of the things that we were using to construct these, again, just very quickly, a couple of definitions. There is a graph cross product. We define G cross H as a graph with vertex set, V of G cross V of H. And then we define the edge relation. So we're going to define an edge between UIVI and UJVJ with the following conditions. If any one of the following conditions holds, right? So if there's an edge between UI and UJ, and VI and VJ are the same vertex, or flipped around, right? UI and UJ are the same vertex, and VI VJ is an edge, or there's an edge between both UI UJ and VI VJ. And I wish I had put a diagram of this up there, but there isn't. Yeah, question?
If you cross two edges, do you get the K4?
Yes.
Okay.
Yes. Good example. And so then, again, the idea of vertex splitting, which of course what I kind of did over here with the Petersons graph, right? You want to sort of, we split a vertex to form graph G sub V, duplicating the vertex by adding V sub naught and connecting it to all the vertices adjacent to V. Not quite vertex splitting over there, but nevertheless. So the result that we had to do with complete graphs. And the last statement here, of course, is the theorem that we came up with. The previous two were previous results used in the proof of this. And so just to kind of get to the end result, the idea was our complete graphs K class 0. And we were able to show that for each K, there's going to be some n such that the complete graph on n vertices can be edge partitioned into K cyclically symmetric 2D3C subgraphs. And therefore, it's K class 0. And so in this case, so for a 2 class 0 case, if K is equal to 2, all we need is n equals 9 to satisfy that condition. So if I have a K9 down here, right, I can basically, if you will, symmetrically partition the edges so that both of those subgraphs are 2 class or class 0 graphs. And so again, just another diagram for partitioning this up. And so given a K, we can find a complete graph large enough so that we can partition that complete graph into K class 0 subgraphs. It's nice, but it basically just deals with complete graphs. And I think this is one of the reasons we've been holding back on this. We did also kind of show it for, like, if you remove 1 or 2 edges, strategically remove 1 or 2 edges. So if we have something that's almost complete, we could also show that it can be partitioned. That doesn't really gain us much at that point. And so there really still are a bunch of questions. Are there other types of graphs out there that can be classified as K class 0 subgraphs? Are there necessary and sufficient conditions that exist that can identify these graphs? And again, I'm talking about symmetric, breaking it up in some kind of a symmetric pattern. Doesn't have to be symmetric. Is it possible to come up with a K class 0 graph that is partitioned into K class 0 subgraphs that is not necessarily symmetric? Now, I don't think these are necessarily easy questions, but this is something we're continuing to work on. We're hoping at least to find another family before we head off and rush, to publish the result beyond what we have. But that's kind of where we are with this. For the last 5 minutes or so, something more recent. This was, again, started out as an REU project. IKEA Richburg from a couple of years ago worked on this with me. He's continued to work on it. We have since picked up Kellen Myers. Some of you might know Kellen has been working on this. We just recently, within the last couple of weeks, came up with some results. So it's not clean, but again, just to repeat, a directed graph is a graph with directed edges. I'm going to introduce the idea of a competition graph. And so a competition graph has the same vertex set as the digraph, except I'm now going to draw a non-directed edge between two vertices if they are in competition. So if you think about the food web, B and D both feed on E, right? Again, the arrows are going this way, so E is the food source for both B and D, so B and D are in competition with each other. And so the competition graph is going to show which species are in competition for the same food source. You can write it as an interval graph. Again, I don't want to spend too much time, but again, if you're looking at, if intervals are sort of overlapping, then they would be in competition for the same food source. You can represent then this as, this would be the competition graph for that sort of simple ecological example. I should mention here that Dr. Roberts did a lot of early work on this, and I won't define it here, but the idea of boxicity was a term that he coined. And this problem originally came from a conversation with Dr. Roberts. And the problem that we were working on was the following. I'm going to define a doubly partial order, right? So I basically have a partial order, and a doubly partial order is a set of ordered pairs. And the condition is that I have an edge, a directed edge, going from ZW to XY if X is less than Z and Y is less than W. So the X coordinate is less than the corresponding X coordinate, and same with the Y. And so a digraph is called a doubly partial order if D is isomorphic to a digraph of a doubly partial order relation on R2. And so the problem was, suppose we've got a digraph that is a doubly partial order, right, like this example here. Can we identify the forbidden subgraphs of the corresponding competition graph? So constructing a competition graph, can we identify forbidden subgraphs as a result? And again, just some quick preliminary results. The REU student came up with a couple of obvious ones, and like I said, just in the last couple of weeks, we've been able to sort of completely classify on a doubly partial, actually on an n tuple order graph, the set of forbidden subgraphs. But it still leaves some questions. For example, what about other posets? I mean, this is one particular type of poset that we're looking at. Were I to do the same thing with, say, another poset with a different set of restrictions, would I still get the same set of forbidden subgraphs? Right? And so I hate to leave that there, rather vague, but more to come on that. And so that basically is it.
Very nice.